Primeira coisa, antes de você ver, tá nos gravando, então vai estar no link. Então, se você quer fazer uma pergunta, você lembra que você vai ser gravado. Mas tudo bem, não são histórias, essas perguntas. Hoje temos o grande prazer de ter a Simona Procacci. Ela é um pouco da Itália, um pouco da Suíça, mas fiz a graduação em Universidade o doutorado também, e agora está o pós-doc na Universidade de Rio de Janeiro. Ela vai falar para nós sobre o Dark Sector no Abelian.
Muito obrigada. Yeah, thanks for the opportunity to present my work here. Okay, thanks for the lights. Yeah. Okay. Yeah, I'm really enjoying my experience in the Brazilian community. Really nice here, and I hope it will be something back. And I know I'm aware that my title is a bit obscure, and I'm really glad you are here and despite of my choice. But the idea I would like to present, I think, is quite simple. So yeah, let's get to it. And just before I start, I mentioned after we finish this work, a very similar one appears. So if you find it interesting, please check also of this guide. Okay, let's start. Since the name of your department has something with chronology to do, I'll start with chronology. And in my talk, we will be mostly in the, like always in the early universe. Early means for me before the emission of the cosmic microwave background. And in fact, most of what we have predicted in the first place for the universe or for the evolution of the universe before the CMB was precisely to explain the features of the CMB. And I will start by mentioning one of those features. This is a plot you might have seen quite often already. It is the correlation function, this one, between the fluctuations in the temperature of the CMB surface. So we have large frequencies measured on the right, large frequencies in small distances, and on the left we have very large distances in small frequencies. And this correlation function is really amazing because if you think about that from statistical physics and so on, we are used to have large correlations on very small distances. So this is like really counterintuitive. So there was a puzzle for a while. How can we explain having such large correlations on large distances and almost no correlation if we go to the wave? Nowadays we have a paradigm of something. So let's go to the next one. I can say because I don't have animation for yet. We'll have to go one more. It's also okay. Okay, let's keep on. Let's try going forward for a second. Maybe you are right from the beginning.
Ela tem um documento de PDF antes do programa. Ele vai abrir de novo o arquivo.
John. Sim. Se for, aqui. just a second, guys. Sorry. Problema técnico.
Okay, so here for me say just interrupt me at any time. We have plenty of time.
Well, which one is it?
And the last verse.
Let me, just a second, let me. Go.
Yes,
Okay, perfect.
here we are.
Sorry about that. Okay.
Okay, so nowadays we have a paradigm to explain or to model the how large correlations on large scale could have been stored within the universe. Oh, and the idea is that this, at some point in the early universe, the expansion of the universe was accelerated much faster than in the other epochs. Then the region, so this is the line that catches the emission of CMB photons. If this accelerated expansion period was long enough at the right moment, we might causally connect the entire CMB portion that is there. And this is the model of inflation, but it's still at the level of being a model. We don't have direct growth of inflation. And now I will just sketch you a question about inflation that we will meet later. So if we describe our universe as being on large scale, more or less homogeneous and isotropic and expanding, then this metric A is the scale factor that describes the expansion of the universe. Apart from A, it looks like approximately so flat in this case. And then for the matter content, I usually take a perfect fluid. Since we are in a homogeneous and isotropic approximation, E is energy density, P is the pressure, and they are related via equation of state. Okay, and then also I call H the expansion rate of the universe, the Hubble rate. So how does the inflation work? You take this answer, this metric, and we plug in Einstein's equation. The result are these two equations, but the Friedmann equation. And the really important thing now is to look at the second one, where we can see, so A was the scale factor of the universe. So if A dot is negative, we have an accelerated expansion. This is what we want in inflation. But if it will have the right-hand side be negative, we need a negative pressure. And the easiest way to parameterize the negative pressure is to take a scalar field, so very simple Lagrangian, some self-amplifying. And now if we derive the pressure and the energy density from the Lagrangian, we see that having a very high potential energy would precisely is a negative pressure. This also means that, okay, we are suppressing kinetic energy for a while. And if the potential energy is almost constant for a period, then the energy that we plug in the first equation is almost constant. The first equation describes the expansion rate, and having an almost constant expansion rate means an exponential expansion. So this is the idea of inflation. It is very simple, so we can already have a picture in mind of how the scalar field evolves. It is evolving very slowly, as long as the potential energy is dominating, but at some point, assuming the potential has a minimum, as we approach the minimum of the potential, then the kinetic energy is not negligible anymore, and this period ends. So the scalar field will start oscillating a normal massive scalar field. Okay, this is inflation, and this is what I sketched at the very beginning of my picture. And so this is time that we estimate being 10 to the minus 32 seconds. This means almost nothing because we find the result 0. This is simply where we cannot count back anymore in time. So inflation is defined to explain the fluctuations of activity or time scales are given by CMB. But on the other hand, just from this other model, we can also make some predictions for what happened before the CMB. And this is well studied physics. So we can go in a quite robust way, probably at least 15 orders of magnitude in time before the CMB. But we are still not covering a gap of 20 orders of magnitude before maybe I don't know, electric symmetry breaking and inflation. So this is a huge gap. This is a fairly unexplored period of the evolution of our universe. And it's the period that puzzles me the most. And I think it's a very important and interesting question to ask for the validity of inflation, if we can match the prediction in the standard model with the of inflation and build or somehow reconnect with the prediction. And what is crazy about that is that on the right hand here, we are really dealing with a very rich environment. From the system, we have a lot of different fields. They are interacting with each other at very high temperatures, high densities, and therefore the interactions are highly nonlinear. We cannot use very much to the physics. On the other hand, what I was describing before was defining only a superscalar field, no temperature, nothing. And you can also imagine that it's such an incredible expansion. Any other field that would be around and not able to the interval would be simply very. So it's probably being suppressed afterwards. So I think it's really a question that goes beyond modern building cosmology, that requires some skills also from the quantum computer point of view, and which will also describe normalization. There are many open problems to solve there. And of course, I'm not going to cover all of them. We decided to tackle this transition period by also addressing another accepted speculation, I would say, in particular cosmology, which is dark matter. So the idea that at some point a dark sector should appear and remain stable as predicted by independent detections. So this is how it works. It's really simple. We have still the inflaton field that I was introducing before. We assume that it interacts very weakly with a dark sector. So that dark for me means something we cannot measure. It's not from the model. And this other heat bus, dark heat bus, will then itself use some energy to source the standard model what we observe. But partially also will remain stable and form dark matter. Like a two-stage. And now if we want to write the Lagrangian of everything, in this case, of course, we have the kinetic terms for the different sectors. So here we have inflaton, dark sectors on the model, and we have self-interactions also in the dark sector in the standard model. But then we need some interaction terms. So J is for me a composite dark operator of whatever type that couples to the inflaton, and then we also have some quantum interactions between the among the visible and the dark sector. And having a Lagrangian at hand, we can already guess how the evolution equations for the different energy densities are. in particular, what we expect is to have friction, the friction curve that subtracts energy from the inflaton field and sources the dark heat out, the dark sector, and at the same time there is some decay of the dark sectors that give rise to the standard model, to the inflaton sector. And all of this happens, of course, in an expanding universe. So we have this H appearing in the equations. This is like a friction. And it depends very dynamically on how the evolution in the energy density goes. So from the equation I was showing before. So this means that this set of three equations is highly coupled and non-linear. So we need to solve this numerically. And of course, to solve it, we also need an answer for the dark sector because we need an equation of state for the dark sector. We need to compute the friction there and the decay. So what I will do now is pick a concrete example, but I will try to be as model independent as possible, but I think it is this child was motivated because we can really compute a lot of things concretely using the knowledge we have about the standard model, non-Abelian sector, and it's a way for me to show how one could do some precision cosmology even in the early universe. I think it's just a nice. Okay, non-Abelian dark sector, and now so the choice is a bit trivial. First of all, why do we choose a gauge sector? Well, there is a very special coupling which is discussed a lot beyond the standard model physics. And this is a coupling of this type. So this is not a normal kinetic term for the gauge sector. Here we have F dual, and this the special property of this interaction term is that we can rewrite it as a total derivative. So it is, if our scalar field phi is not dynamical, it might not contribute to the equation. It is now I'm doing a non-trivial step, but one can show that using this property that the way this interaction term affects the equation of motion for the inflaton field is such that we don't get any large correction on the dynamics of the scalar field. So we get a friction term, which is what we want, but we don't get any thermal mass correction. It would be bad because if you remember, any corrections to the mass of the inflaton would affect the shape of the potential for inflation, so the change of the dynamics. This is phenomenological choice. I would say it's just it works for inflation and nice. And also we can use some results from standard model physics to derive the friction terms that correspond to this operator. And it is by its own a very interesting problem to evaluate this friction term because depending on the scales we are probing, so we think of the scalar fields, which is vast that are between interacting, really like a test particle, and we evaluate friction in the usual sense. So it is the correlation function of the operator, and then of course we have different contributions. We go at very small temperatures, then only the vacuum contribution, vacuum decay of the inflaton to gluons, dark gluons will contribute. If we increase the temperature, then we have some self-enhancement. Self-enhancement is that if you are in a plasma, there is some effective interaction that is self-amplifying the process. Okay, so we can be very concrete. The inflation works, but then why do we choose non-Abelian? In general, being non-Abelian has many advantages, despite the large number of diagrams and other things we need to compute usually. The first important point for us was that if you have non-Abelian gauge fields, they are believed to thermalize very rapidly. So it is a fairly good approximation to work with local thermal equilibrium, and also to assume that we don't have large dependence on the initial conditions. And on the other hand, having like these non-Abelian interactions also means that there might be a critical scale below which the self-interaction within our heat path becomes strong. So this is what I'm showing here. Those are the thermodynamic functions for SUN gauge sector, taken from lattice results. Okay, as long as we are above the critical temperature, in fact, we can obtain the curves using derivative physics. But as soon as we reach the critical scale, so the heat capacity drops drastically. So we need the full non-perturbative information to parameterize it. And there is a lot of interesting physics going on. And this is what I will spoil now. So we should then ask ourselves, right? So above the critical temperature, the system seems to be well designed. So I said heat bar, so it's easier to shift the energy from one temperature to the other. But what happens below the critical temperature? So as I'm not adding any fermions or other particles in the dark sector, once you go below the critical temperature, what you have are very strongly interacting dark gluons, so we call them dark blue balls. And in general, so we are building those states from the self-interaction of vectors, so they have Lorentz groups. It means that they also transform under Lorentz transformations, and usually they are transcribed for their spin, parity, and charge communication. So this is the spectrum, and also for thermal mass. And here, so on the left of the line are the states that are C even, on the right are C odd. And I do this distinction because it's the most interesting for our purposes. You think about it, so, C even states, they can interact to standard model state, C even model state, already with lower dimension operators diagrams, lower dimension. It means that the decay width goes with the confinement state to the power of 5. On the other hand, if I have C odd states, in order to talk to the standard model operators, we need to first combine them. They show up in a composite way, and the lowest operator I can write, as I mentioned, 8. It means that decay width scales with the combined scale with 9. And I'm parameterizing with some scales of new physics in both cases. So you might see where I'm going, because if we have C even state, then the decay standard model is efficient, and we might be able to source enough standard model. And on the other hand, the odd states, they could maybe be stable enough to remain around and build the dark matter. Okay, and of course, so on top of this effect, all the states have complicated self interactions among each other. So for the first analysis, we just included 3 global states, meaning the first 2 less massive even state and the first odd state. Okay, and now the next question we should ask ourselves is, taking the combined scale of the dark sector and the scale of physics as 3 parameters, does it happen, or when does it happen that a phase transition really occurs in our scenario? And now there is the spoiler of the dynamics. Of course, I'm showing you already the good parameter space, and I will explain at the end what good means. So, but in the region of parameter space that we are interested in, if we solve the evolution equations I was showing before, and I already showed all the details to do it completely with above the critical temperature. So if we do that, it really looks like what we wanted to have. So the blue line is the energy density of the inflaton field, which is really the dominating contribution. The total energy density is the order of magnitude of the next one. And it's almost constant for a short period of time, and then it starts behaving like something without pressure or matter. It's oscillating. At the same time, the red curve is the dark sector, which is well above the critical temperature here, and it has some maximal temperature at the end of inflation. And at some point, it will dominate when the decay of the inflaton part of the inflaton condensate catch up with the expansion of the. And something happens that we were not even here hoping for, and it is that this moment where the inflaton is completely decaying away coincides quite well with the end of the phase transition. So the phase transition happens here, and after that moment, we cannot assume thermalization in a safe way. But at least we can get rid of the. Okay, so it seems that our scenario is consistent above the critical temperature. This is for a long while, and now we can start playing with the glucose. And playing with the glucose means, okay, we drop the first equation. We still have these two equations to solve. Okay, before we were solving directly for the energy density and parameterizing the dark sector with the temperature, that's we could assume the validation. But now below, the dark sector is not or should exit thermal equilibrium, as we have strongly interacting states, and therefore we will have many more variables. So these are the two equations. In particular, now the dark sector, okay, might still have some motion of the temperature for a while, but also it should depend on the dynamics of the glucose. So in particular, we want to capture at the end how many even states, how many stable states are still around, or are they all gone, and are the odd states stable enough? So we have here already one variable, and here I said I take 3 glucose, so 4 variables, and still the energy density of the standard model, way too many variables for 2 equations. So we need some more equations, and of course those are Boltzmann equations for the glucose states. And we write down, okay, they are some decay ways that are dependent on the quantum numbers. But of course, like I'm not writing the full equations because in principle, those equations have a tower of self-interactions between the different glucose states. And the problem is that each of those interactions comes with as many unknown coefficients. But as said, so if we think about the problem, not all of those interactions are really relevant. They are all important, but we can do some, we can cut the series by thinking that we want to know how many stable states remain at the end. So we want to know how many of the even states switch to odd states through decay. And also, so this means getting all the two interactions between even and odd states. But also we want to know if there are frequency or number changing processes that reduce the number of even states. So these are the interactions we consider for our first analysis. So these are the 52 looks more or less like this. Of course, only even states have 52 interactions, and then we have 52 interactions. And they really should describe how we depart from an equilibrium distribution. And all of that is then regulated by the strength of the cross sections. And the cross sections, of course, depend on what we have input for the confinement scale. In particular, they are inversely proportional to the confinement scale. But so one of the difficulties of the setup is that global states are not yet well studied. So we have some lattice inputs, but not for all the cross sections. No, lattice people tell them to work on it. And for the moment, we need to rely on larger expansion for naive dimensional analysis. And this is the result. This is the dynamics of the global. So it describes how the energy density of the global state departure from the equilibrium distribution. The blue line above is the even state. So one of the states we want to decay at the end of our evolution. The dashed line is the equilibrium distribution. So it's the number density is following equilibrium for a while. And at some point, the blue line remains like at larger values, meaning it's not decaying, would be temperature would vanish. And this happens precisely when the C2 interactions are not efficient anymore. And at the same time, so if you look at the red curve, this describes the number density of the odds for the stable states. And when the other states are out of equilibrium, so this affects the full system because they interact, so to have the motivation to maintain the equilibrium, should have efficient interactions in your system. So what happens is that we have a good new equilibrium, so we develop a chemical potential, which is followed for another moment because we still have 22 interactions that are efficient. Of course, now if I would add all the other interactions that in principle are in the Boltzmann equation, it might take longer to reach this moment and this second moment. And this is a first approximation, and what we are really interested in is to have the value of the ratio between the number density of the stable states at the end of this picture from the beginning. So as I said, so this is again a specific choice for the good parameter space. The picture would change since the cross section changes with different confinement states, and in particular, if we go to smaller confinement states, we will have more efficient interactions. More efficient interactions means taking longer to departure from equilibrium and therefore having less dark matter. Okay, this is not the only effect. If we go back to the full picture, and what the plot I was showing before is like what enters the red line or helps to compute the red line for the just very first moment after the evolution. And now we can also think that if we go to lower confinement scales, then this critical temperature is reached later, and therefore we even start the freeze-off dynamics at later energies. And before at the end, we also had less energy, so we had less contact. We have a quite significant dependence on the parameters, and what we do with that is that we read out the energy that remains in the dark sector once all unstable states have decayed. So you can see it from the curve. So here we just have stable states remaining around. And once we compute how much it dilutes to the value we observe for dark matter, we can compare with the observed abundance. So this gives us an upper bound for the confinement scale. We also have another upper bound of the confinement scale that is coming from the requirement that, okay, we still have dark glucose around, and now we want them to be stable enough and the intersections of the dark matter today. So we compute the lifetime of the stable balls and compare with the predicted lifetime. This is not a very precise one, but orders of magnitude will give another indication of what would be a maximum confinement. And also to close the parameter space, we have to have a lower bound, and this exists because from Big Bang nucleosynthesis, we know that the nucleosynthesis formation of the nuclei was efficient only if the temperature at that time was above 4 megahertz. So I'm not saying that here we are at Big Bang nucleosynthesis, but for sure, once the standard model starts dominating, it must have at least this temperature. So this gives us a lower bound on the confinement scale, because if we go to a higher confinement scale, then the full picture is translated, and the standard model will start dominating at higher. So this is the parameter space we obtain. And in this quite a predictive parameter space, so the order of magnitude of our parameters is our scale of new physics for the water interactions between dark matter and standard model, and the confinement scale for the dark sector. They both have some fixed order of magnitude, and we still have an open parameter space, which I guess is good news, and is, as said, bounded from above by the relative abundance of dark matter, by the lifetime of dark matter, and from below by the temperature of standard model. So now there are different conclusions one could take from this picture. And I think it depends a lot on what is your personal point of view. So if you are very optimistic about inflation, well, the good news is that we have a quite concrete example to map a quite generic model of inflation to the advent of standard model using a non-Abelian gauge factor, and it might work well with a generic gauge factor. So it could be applied in different sources. But then if you're rather skeptical about inflation, I think a very fair point is that, okay, we have an example and we have another parameter space, but the parameter space suffers from huge orders of magnitude uncertainties from the theoretical point of view. So I think this is still personal, but in any case, the take-home message, I think, is that really so the transition between a vacuum dominated expanding universe and the additional dominant universe we expect later is a very interesting period, and contains a lot of nice physics, and also that it is worth to investigate more non-Abelian physics. So and with that, thank you.
Any questions?
Os compositores da massa de balls is the
And it's proportional to the confinement state.
but not the typical mass.
And like the mass spectrum. So usually normalized by the lightest global state, and the lightest global state is 5 times the confined state. We are in, I haven't said that, but we are using actually results for age group for having some numerical.
So you have a phase transition for the transition from vacuum to radiation, right? It's maybe a naive question, but how does this differ from the QCD phase transition from the CDM?
So this confinement presentation?
Yeah.
Okay, the main difference here is that I don't have second.
First order.
You don't have electrically for or you have photons. You
Yeah,
have photons, no.
I mean, the standard model should be represented in this full glory, but it's interacting probably only quickly via mixed photon interactions, but otherwise for the dark sector, I only have spectrum. So, but I mean, this was the main idea I want to add to it.
Actually, I have a question here related to, because if you only have gluons first order, right? And if it's first order, it has a mixed phase.
Yes, this is the gray line.
Gray line is
Gray
mixed
line.
phase. The mixed phase also generates inflation, right? It has, or not.
I've just learned that from you, but I don't have Bible from.
No, but you don't need, like, the inflation that was done in the eighties with Alan Booth. He had a first order phase transition, right? The
Yeah.
mixed phase, you didn't have this. Yeah.
It has, but it was a basic definition of our Taylor field.
Yeah.
And it was a quite strong one. I'm not sure, but I think one could investigate that, but like on the top of my head, I would say that this phase transition, okay, it was called a confinement phase transition. It's confining. It's from the phase transition dynamics point of view, it should be a bit fun. So maybe it's not something to do about.
Some bottom inflation, but some-
Yeah.
That is like that we have the closeness.
Yeah.
I didn't understand that. Those results are from the last
Yeah. Yes, absolutely.
SUT.
quenched, simply, right?
Yeah. Exactly. So, yeah, it's group work.
Then you are using exactly the same values for the next. You are calculation, not for the.
Yes, yes. No, I mean, not necessarily for the method, but the relation between mass and confinement phase. Like I have the confinement phase is entering, like, yeah. So this is how I then, okay, forget about the last part of the decay, but the rest is what is my energy density for the dark sector, and it's given by all the, but this is a crude approximation because I have like I should have the full spectrum of all the glucose they do from one but I'm matching what I have above the phase transition to like a spectrum of glucose. And the confinement phase entering the mass, and then the real variables are some for.
What is the value of your confinement scale that you are saying? What is the value that you are using for your confinement?
It's a parameter. I solve the evolution.
And in the end, what's the value that you get?
It's very high, like yeah, large gigaelectron balls. Yeah.
That was 6 GeV.
Yeah, so 10⁻⁶ large mass. So it's really like not.
To follow up the question, so you also only consider the directions in equilibrium, right? Don't consider other
Okay.
Dynamics.
Well, so this group of dynamics should really capture like the departure from equilibrium. I have some. Those are the interactions. I'm solving for the ends, the number densities, and equilibrium is parameterized by the confinement scale and the temperature that I'm also solving for.
Okay.
So after, like at some point, the temperature drops, so this part is becoming negligible, and then I
I see.
have number densities that are like unknown.
Because what I'm thinking is, can you say something about the body symmetry in the universe?
Maybe I can, but you can. Yeah. Okay, it's another interesting question. Also because we thought first of the phase transition and they are known to generate from higher effect. So yeah.
So the matter is not stable, just very long way, right?
Yeah.
In your parameter space of the function that have five life of the unit.
Okay, so you're asking about the real markets. We really much we thought there was a question for different combined scales and kind of new physics, and but the way we choose them is that they always match physics. Yeah, we 27. This bound is not so precise from experiments to depend how you compute the because it's indirect detection and it really depends what do you assume for your lab scenarios. So it might I think it's something we are looking at now, but it might vary one or two orders of magnitude depending how to assume the document to enter your indirect detection.
This is like, you know, the GWST is far away, any simulation, how the vision for the
Yeah.
galaxy changes. Like that.
I can I'm also thinking about
Because then, you know, I mean, what you're saying is that lifetime of the universe, a lot of them, maybe we don't see themselves, so we see it without seeing.
Yeah.
I'm not that familiar with patients, so could you explain again why you need to connect the inflaton to the dark side?
You think so? Okay. So the usual picture is to jump directly to have the user is equal to you the dynamic of inflation being phi and the exponential. It's maybe like this, I take the evolution from here, not only the stating, and then you read the universe through the calculation of a therapy computation. But if, and I mean, if my point, you can come to the scalar field here, otherwise it's directly, because going to another sector. But since inflation was supposed to predict the scalar perturbations of the CMP, you should make sure that it's not destroyed those predictions. And it turned out that in fact it is not an easy exercise to find the very venture that allows you like coupling with real fundamental fields that have the masses and all the properties, you know, and do not affect the prediction. It is still possible, but we come up with very potential shapes for the relation. You can do that. So just going ahead to find thank you.
Well, Simona is here for the rest of that. Let's thank you very much.